Studies Section 11, the chi-square distribution. All of the inferential statistics we covered in the previous study session are called parametric statistics. To use these statistics, you will make some assumptions about the distribution they come from, such as they are normally distributed with parametric statistics. You will also deal with data for the variable that is at the interval or ratio level of measurement. That is test scores, physical measurement, etc. You shall now consider a widely used non-parametric test. Chi-square. Which we can use with data at the nominal level. That that is classifactory. The symbol X is the Greek letter chi. The sampling distribution of X squared is called S-squared distribution. Learning outcomes for study section 11. When you have studied this session, you should be able to list the properties of the chi-square distribution, list the conditions for the applications of chi-square test, list the types of chi-square, compute chi-square probabilities, and list some applications of chi-square test. Chi-square distribution. The chi-square S-square distribution is obtained from the values of the ratio of the sample variance and population variance multiplied by the degrees of freedom n. This occurs when the population is normally distributed with population variance. X squared is equal to properties of the chi-square distribution. Chi-square is non-negative. It is the ratio of two non-negative values. Therefore, it must be non-negative itself. Some of the properties are as follows. Chi-square is non-symmetric. There are many different chi-square distributions, one for each degree of freedom. The degree of freedom when working with a single population variance is n-1. 1. For degrees of freedom greater or equal to 30, the S-squared curve approximate to the normal curve. 2. The mean of the chi-square distribution is n. And the variance is 2n. Types of chi-square. The following are types of chi-square. Pearson's chi-square. It is It is by it is by it is by far by far the 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 most the most the most the most the most the most most common type of chi-square significance test. If simply chi-square is mentioned, it it is probably Pearson's chi-square. This statistic is used to test the hypothesis of no association of columns and rows in tabular data. It can be used even with nominal data. Yates correction. It is an arbitrary conservative adjustment to chi-square when applied to tables with one or more cells with frequencies less than 5. It is only applied to 2 by 2 tables. Some authors also apply it to all 2 by 2 tables, since the correction gives a better approximation to the binomial distribution. Yates correction is conservative in the sense of making it more difficult to establish significance. Chi-square goodness of fit test. The goodness of fit test is simply a different use of Pearsonian chi-square. It is used to test whether or not and observe distribution conforms to any other distribution such as one based on theory. X if the observed distribution is is not significantly different from a normal distribution or one based on some other known distribution x if the observed distribution is not significantly different from a known national distribution based on census data. Likelihood ratio chi-square. It is an alternative procedure to test the hypothesis of no association of columns and rows in nominal level tabular data. It is based on maximum likelihood estimation, though computed differently. Likelihood ratio chi-square is interpreted the same way for large samples. Likelihood ratio chi-square will be closing result to Pearson chi-square. Even for smaller samples, it really leads to different substantive results. Mantel-Haenszel chi-square. It is also called the Mantel-Haenszel test for linear association or linear by linear association chi-square. Unlike ordinary and likelihood ratio chi-square, Mantel-Haenszel chi-square is an ordinary measure of significance. It is preferred when testing the significance of linear relationship between two ordinal variables, since it is more powerful than Pearson chi-square, more likely to establish linear association. Mantel D. Conditions for the applications of S-squared test. As mentioned before, chi-square is a non-parametric test. It does not require the sample data to be more or less normally distributed. As parametric tests like t-test do. Although it relies on the assumption that the variable is normally distributed in the population from which the sample is drawn. chi-square in spite of the above does have some requirements. 1. The sample must be randomly drawn from the population. 2. Data must be reported in raw frequencies, not percentages, or ratios. 3. Measured variables must be independent. 4. Values categories on independent and dependent variables must be mutually exclusive and exhaustive. 5. Observed frequencies cannot be too small. It should contain at least five observations. The chi-square test statistic